Hi everyone, after going over the basic concepts of game theory, we are now going to formally define what a Nash equilibrium is, how to find it, and its properties. I'll start with a disclaimer. I do not allow this content to be published without my consent. I will take this content down if I see it uploaded anywhere online and report whoever uploaded it. So, let's start with Nash equilibrium. A Nash equilibrium is a profile of strategies, very important, such that each player's strategy is the best response to every other player's strategy. I already mentioned the idea of what a best response is. So, a Nash equilibrium is a profile of strategies, it's a list of strategies, such that each strategy is the best response to all the other strategies played by the other players. Imagine, for instance, that you have a two-player game. It is a profile of strategies, remember, not the same things as actions. I'm going to call those strategies S1 and S2, strategy for player 1, strategy for player 2, such that strategy 1, S1 is the best response to S2, and S2 is the best response to S1. As in, S1 maximizes the payoff of player 1 given player 2 plays S2, and vice versa. Okay? Now, a Nash equilibrium can be in pure strategies, you play something with a probability equal to 1, or in mixed strategies. You play different strategies with different probabilities. You put some randomization in the way you play your strategies. Don't worry about this for now. Just stick to pure strategies for now. I will go over mixed strategies in part 4. It's going to be in 2 weeks. So, in a Nash equilibrium, which I will call NE for the rest of the course, each player chooses a strategy that maximizes their expected payoff given the strategies employed by other players. If you remember what I said about dominated and dominant strategies, I talked about a strategy being a best response regardless of what the other player does. Here, I am looking at what the other player is doing. So each player's equilibrium strategy is a best response to the equilibrium strategy of the other player. Let's go back to the prisoner's dilemma. Here, confess is a best response to confess. So row playing confess is the best response when column plays confess. And column playing confess is the best response to row playing confess as well. They both play a best response to each other, which is why those two payoffs are underlined, and which is why confess is the Nash equilibrium. Forgive my typo here, it should be confess as well. So confess satisfies the definition of a Nash equilibrium and is the only profile of strategies that does so in this game. For instance, when Colin plays not confess, row wants to play confess. So row playing confess is the best response to Colin playing not confess. That goes one way. However, if you go the other way, it doesn't work. Colin playing not confess is not a best response to row playing confess. When row plays confess, Colin wants to play confess as well. So the concept of Nash equilibrium comes from John Nash, who died in 2015. I think it was a car accident. He won the Nobel Prize in Economics in 1994 with two other game theorists, Selton and Harsanyi. I won't talk about them in this course, but we are going to study games that they invented. We are going to study concepts that they helped invent. I just won't name them. There is also a movie with, Beautiful Mind with 4 Oscars. Yeah, I thought it was 1, but that's 4. And he was originally a mathematics professor. He is a mathematical genius. And he also struggled with paranoid type of schizophrenia. Actually, online, if you type John Nash recommendation letter, you can find a recommendation letter that a professor at, where was he? He went to Princeton for his studies. So before Princeton, he might have been at MIT or Columbia or another big school. He had a reference letter for his master's program in mathematics to enter Princeton. The letter literally says, it's a professor who writes this letter for Nash, that says he literally is a mathematical genius. You can find it in the letter. It's pretty rare. You don't find reference letters like that very often. It's very rare that professors, like fully fledged professors, researchers, internationally famous, commit that much to the quality of a student. So, interestingly, if you watch the movie, well, it's a bit romanced, but there is a huge part of his life where he struggled because of schizophrenia. So in the movie, you see that he has a couple of, he is struggling with different characters in his life that nobody else sees and that he believes are real. And that made him lose his position for a while as a professor. He was writing his theories on Windows at the library, so he was still doing research, but he was not employed as an instructor, as a lecturer, or as a professor at the university for the longest time. He was recognized eventually later, and he also has big contributions in mathematics, but those contributions are too advanced for us. I heard about one of them. I can understand what's going on, but it's a bit too high level for us. Now, I mentioned in the previous lecture that some profiles of strategies could be Nash equilibria, for instance, the coordination game, but they might not be the outcome. So, Nash equilibria don't always predict what is going to be played. So, why do we study it? Why do we care about this concept so much? And you will see that we'll go over Nash equilibria over and over again during this chapter. The idea is that, first of all, if players play a Nash equilibrium, so if they play the strategies of a Nash equilibrium, no one has an incentive to change their behavior. No one has an incentive to play something else or have second thoughts. So that represents the idea of no regrets. Once you play the Nash equilibrium strategy, and the other player does as well, none of you regret what you did. First of all. Other potential outcomes do not have this property. If you think about the coordination game, where Rosia and Tom, those were the players, meet at different locations, well, they don't meet, they go to different locations, then both of them will regret not having gone to the other location. So if an outcome is not a Nash equilibrium, then at least one player wishes to reconsider his strategy. One player at least wishes he had done something else. So outcomes that are not a Nash equilibrium involve mistakes from at least one player. It's this idea that one player at least regrets, so he thinks he made a mistake. And so, players which are sophisticated, highly rational, they can anticipate many rounds of thinking about what the other one is doing. I know that you know that I know. Should be able to eventually play a Nash equilibrium. And when I say eventually, I mean that eventually they're going to learn to play a Nash Equilibrium. In fact, there have been some experiments on some people who played games like Prisoner's Dilemmas, coordination games, and so on. And after playing many times in a row, they eventually end up playing a Nash Equilibrium, and once they play it once, they tend to keep playing it for many periods after. So sometimes it takes time to understand the rules, make sure to understand the mechanics of the payoff matrix. So Nash Equilibria are not played at the beginning, and eventually there is some kind of coordination that happens, and players eventually converge to Nash Equilibria. The other thing is, if a game is dominance solvable, so we can find one solution, one equilibrium using iterated elimination of strictly dominated strategies, then the outcome is the only Nash Equilibrium of the game, and it is also the outcome. So it is a prediction. Careful, however. Stick to the definition of a Nash Equilibrium, the strict definition. A Nash Equilibrium is not the jointly best outcome for all players. For example, in the Prisoner's Dilemma, the jointly best outcome was the opposite. This is the one where they do not confess. They help each other by not confessing and say, I don't know what happened. I was there. I was at the crime scene randomly. It was an accident. So I know nothing. It is not a situation where players always choose the same action. We went over games where players can have different actions. I went over a game where Colin can play left, center, right, and Ro could play top, middle, bottom. And we had one Nash Equilibrium in this case. And it is not a unique outcome either. First of all, it's not necessarily an outcome, and it is not necessarily unique. In the coordination game, we saw that there are two Nash Equilibria. There are two cases where players don't regret their choice given the choice of the other player. How do we find Nash Equilibria? In fact, I already gave you the tips in the previous lecture, but now I'm going to formalize them. The most reliable way to find all the Nash Equilibria is the cell-by-cell inspection method. So you find a match in best responses. Let's go back to the coordination game. We have Rosia, we have Tom. They can go to beaucoup or to matchstick. I always start, it's a personal choice, I always start by who is playing in the row, who is in the row player. Here, it's Tom. Then I grab a pen with the same color as the player. So if both are in black, you can put a color on the side and say, Tom is going to be in blue, Rosia in red, for instance. And then I look at best responses. If Rosia plays beaucoup, Tom can go to beaucoup and get 2, or go to matchstick and get 0. 2 is better than 0. So Tom's best response when Rosia goes to beaucoup is to also go to beaucoup. So I underline the 2 here in the same color as Tom's color to show that when Rosia plays beaucoup, Tom's best response is to play beaucoup. Forget about the red stuff for now, because I am not done with Tom. Then, if Rosia plays matchstick, Tom's best response is to play matchstick. So, I underline this one here in blue to show that when Rosia plays matchstick, Tom's best response is matchstick. Now, I have covered all the best responses by Tom. Note, by the way, that if two payoffs are the same, imagine for instance that here there was a 2, then you can underline both payoffs because both strategies, going to Boku or going to matchstick, in this case would be a best response. Now, I have covered all the best responses for Tom. I can go to Rosia. So I grab a red pen and I think I put myself in the shoes of Rosia. If Tom goes to Boku, what does Rosia want to do? Rosia can go to Boku and get a payoff of 1, or Rosia can get to matchstick and get a payoff of 0. Rosia will prefer to go to Boku, so I underline 1 here, and that's the best response of Rosia when Tom goes to Boku. If Tom goes to matchstick instead, then Rosia prefers to go to matchstick, and I underline 2. Any cell where both payoffs are underlined is going to be a Nash equilibrium. So if you are dealing with a 2x2 game, or at least a 2-player game, then you can just underline the payoffs when there are best responses, and that will get you all the Nash equilibria. Here we have 2 of them. In fact, they are Nash equilibria in pure strategies. I'll get over the mixed strategies in 2 weeks. In both Nash equilibria, here, the players go to the same place. But careful, when I say the parties coordinate, I'm not saying they explicitly talk to each other. I mean, they end up coordinating because they end up going to the same place. But they have no way to communicate about where to meet. It turns out that given their preferences, parties disagree as to which Nash equilibrium should be played. In both cases, they have no regrets. But in one case, Rosia gets a lower payoff. That's if they both go to Boku. Tom is happier because they go to Boku. If instead they end up at matchstick, Tom is the one with a slightly lower payoff, and he wishes they both went to Boku. Remember that the game is simultaneous, and players have no way to communicate here. So, Rosia could go to matchstick thinking, oh, Tom is probably going to go to matchstick. And Tom could think the opposite. Tom might go to Boku thinking Rosia is going to go to Boku. What's going to happen at the end is they're going to end up here. Tom goes to Boku but will be there alone. Rosia goes to matchstick but she'll be alone as well. And their payoffs are 0 and 0 respectively. So, the same way I said what a Nash equilibrium is and is not, here I'm going to talk about what a Nash equilibrium says and doesn't say. The Nash equilibrium first says that if Rosia goes to matchstick, then Tom wants to go to matchstick. And if Tom goes to matchstick, Rosia wants to go to matchstick. So when you have to verify that something is a Nash equilibrium, I could give you a more complicated game where underlying payoffs doesn't work. Then you just have to think, if this player plays this, that's his best response. But when he plays that, is the other player playing a best response as well? So you always have to check back and forth. It has to go both ways. It's a best response to each other, or each other with more players. Imagine you have 10 players. You have to make sure that each player is playing a best response given what the other players are playing. If everybody is playing a best response at the same time, you have a Nash equilibrium. So careful now. It doesn't say that if they play the game, they're going to end up meeting at matchstick or boku. It is not an outcome. As I mentioned before, it is possible that Tom goes to boku and Rosia goes to matchstick. Payoffs are 0 for both. Of course, if they could communicate, they would directly go to the Nash Equilibrium in this case. Imagine one thing, if they could communicate. Imagine not this game, but imagine the prisoner's dilemma. Imagine that the day before playing the prisoner's dilemma, both players agree on cooperating. So they both agree, they both commit to not confessing. What do you think is going to happen? They coordinate on that because it maximizes the sum of their payoffs. What do you think is going to happen? Well, in the case of a prisoner's dilemma, confessing is a dominant strategy. It is the best thing to do no matter what. So if they agree to play not confess, the next day, they still have an incentive to stab each other in the back. One of them could think, oh, the other one is going to not confess, the other one is going to be nice to me. But if I look at my payoffs, I am better off being mean to him to get no jail time at all. And the other one is going to think the same way. So when a strategy is dominant or dominated, when you have dominance solvable games, it is very hard to credibly commit to play a strategy which is dominated. You have all the incentives to commit to that and then stab the other player in the back by playing the dominant strategy. Here, no strategy is dominant nor dominated. They each know that as long as they meet, they're going to have a positive payoff. So they can communicate on where to meet. They could even bargain on what place to meet at. Because Tom would ideally would like to go to boku, but Rosia ideally would like to go to matchstick. Imagine another coordination game. Tom and Rosia again. This time, matchstick is out of the game because maybe the place is closed. They go to another bakery called Small Victory, which I write Small Vic here. It's a pretty nice bakery downtown. They have 2 locations. They make very good things. Tom still prefers boku. And here, Rosia prefers boku as well to Small Vic. But again, they want to meet. This is the first requirement to get a positive payoff. We still have 2 Nash Equilibria, no problem. But given the payoffs, if they could communicate, where do you think they would agree to meet at? They would both say, let's meet at boku, because both think that boku is better than Small Victory. They get a higher payoff from boku than from Small Victory. Coordination games, there are plenty of them. Think about which side of the road to drive on. You have 2 players, each driving their car. They are facing each other. They are coming in opposite directions. And they can choose to drive left or right. You can imagine what will happen if they both decide to meet and both decide to drive left. If they both drive to their left, then they don't crash. If they both decide to drive to their right, they don't crash. If one of them drives to his right and the one coming in the other direction decides to drive to the left, then they're going to meet and crash. Instead of a payoff of 0, you can imagine the payoffs to be highly negative. Again, they coordinate on which direction to drive on. And you can make a bunch of other games like that, adopting a technology standard, and so on and so forth. It could be 2 firms which want to coordinate on which technology standard they want to adopt. if they don't adopt the same, they might compete with each other in a more ruthless way and decrease their profits. Whereas if they adopt the same technology, they might both increase their profits, for instance. In general, coordination games have multiple Nash equilibria. What matters is that they coordinate one way or another. They could coordinate on 1, 2, or more options. In fact, I could make this game bigger by adding the previous bakery, Matchstick, to the mix. And now they have to decide whether to meet at Small Victory, at Beaucoup, or at Matchstick. We would find 3 different Nash equilibria. As long as they meet with each other, no problem. And then maybe if they could communicate, or the first time they could say, okay, this time we met at Small Victory. Next time, just so you know, I prefer if we meet at Beaucoup. And the other player could say, hey, I prefer that too. So next time they would meet at Beaucoup, for instance. Okay? Any questions so far? Okay. So, we cannot predict a unique outcome if there are multiple Nash equilibria, like the coordination game. So how can we select an equilibrium? Games like the ones I showed above have illustrated the need for a solution to coordination problems, because there is still a chance that they don't meet. So, if they cannot communicate, what can we do? Authors have contributed to the game theory literature by suggesting to focus on specific equilibria for one reason or another. For instance, some equilibria may give higher payoffs. So, the one I gave you above, here, naturally, Beaucoup is a Nash equilibrium which is more likely to happen than Small Victory. In fact, in a game like this, players have a higher chance of coordinate because if they look at the payoff matrix, they see that they can think, well, the other player prefers to go to Beaucoup and I also like Beaucoup. So I can imagine that he's going to think the same way. And so if I go to Beaucoup, I'm pretty sure I'm going to meet him there. In the previous example, where one of them preferred Matchstick and the other one preferred Beaucoup, it is a bit harder. One of them might want to be nice and say, oh, I'm going to go to the location that my partner likes better. Sure. But if the partner is thinking the exact same way, they're going to miss each other and they're going to both end up in the location they prefer the least. So, you will need more assumptions in order to predict which Nash equilibrium is more likely to be played. Sometimes some equilibria could be more fair, maybe safer. So you might imagine or you might assume that the other player is going to go for the Nash equilibrium which is more fair. Not the one that gives him a bigger payoff, but maybe the Nash equilibrium that gives higher payoffs overall. Equilibria selection is tightly linked to the player's preferences for efficiency, fairness, revengeful, being selfish, and so on. So we would have to add additional assumptions about what they are going to assume about the other player if we want to predict which Nash equilibrium is going to be played. When I said one player is going to assume the other player is going to do that, that's a kind of assumption I'm adding. Players can make beliefs. It's a more fancy version of game theory than what we are doing now. But players make beliefs about what the other one is going to do. Given the previous game, players Tom and Rosia could both believe that they will go to Beaucoup because they can think, oh, I think my partner is rational, and he knows I prefer beaucoup. I know he prefers beaucoup, so he would be kind of stupid. It would be stupid if he went to small victory. But that would be a more complicated version of a game where we add beliefs to it. It's not something we're going to cover in this course, but beliefs is something we're going to cover in grad school. If you do a master's and in your master's degree there is a game theory course, chances are you're going to go over beliefs. Now, before finishing this lecture, I want to emphasize that Nash equilibria in pure strategies sometimes do not exist. In particular, pure conflict games are games where there will not be a Nash equilibrium in pure strategies. There is a game that I think none of us play or none of us grew up with called matching pennies. It is something that generations before us, maybe our parents, one way or another would play at recess in elementary school. They would each have a penny and they have to flip the penny and show their penny at the same time. If both pennies are on the same side, one player wins. If pennies are on a different side each, then the other player wins. So, for instance here, I took the case where Rho wins when the pennies match. So when Rho shows head and Colin shows head as well, Rho is the one winning one. Imagine it's one penny. Maybe he wins the penny. And Colin is the one losing the penny because the loser is giving the penny to the winner. So whatever gain one player makes is the loss of another player. It's not, by the way, necessarily the same amount. One is the utility, remember? It's not necessarily just money. So when Rho wins, maybe he gets a utility of 1. And when Colin loses, he might, instead of getting a disutility of 1, he might get a disutility of 2 or 3 because he's a sore loser. Why not? If Rho shows heads and Colin shows tails, then Colin is the one having a payoff of 1 and Rho is the one with a loss of 1. If you do the cell by cell inspection, you will never find a cell where both payoffs are underlined. I suggest you to do it again as practice. You will have to do it many times over this course. So the sooner you get comfortable with it, the better. And there are other examples of strictly competitive games. I talked about penalty kicks before. If you kick the ball, you want to kick the ball in the net, to the net, where the goalie is not. This is how you win. So if the goalie goes in one direction and you shoot in the other, you win, he loses. If you kick in one direction and the goalie goes in the same direction, he catches the ball, he wins, and you lose. So any game that involves a winner and a loser, not any, but most games that involve a winner and a loser will in general not have a pure strategy Nash equilibrium. Think about table tennis. You want to hit the ball where the opponent won't be able to return. If the opponent is able to return, he might win the point. So the idea is that penalty kicks or table tennis, you always want the ball to end up in a place where the other player is not. So you want to be unpredictable. If you can be predicted, then the goalie is going to catch the ball and win. Or in a table tennis match, the opponent is going to counter you. So playing a strategy with a probability of 100% in this case doesn't work because it is predictable. If I am the goalie and I know that this guy always shoots at the same spot, I'm gonna dive there and I'm gonna win. Same with table tennis. If I can predict my opponent's next move, then I can counter it and maybe win the point. And this is where mixed strategies are gonna come in. Maybe I'm gonna kick to the right, maybe I'm gonna kick to the left. But not kicking anywhere for sure is going to make sure I don't lose all the time. I might not win all the time either, because my opponent might also sometimes go to the left and sometimes go to the right. Here, matching pennies if you underline the payoffs. And you see no sale has 2 payoffs underlined, so no Nash Equilibrium in pure strategies. But they will in mixed strategies. So any game has at least one Nash Equilibrium of some sort. If it's not pure strategies, it will be mixed strategies, and I will talk about this in 2 weeks. But there is always at least one Nash Equilibrium. That's it for this lecture on Nash Equilibrium. In the next one, we are going to go over more applications of game theory. For instance, competition, public good provision, and so on and so forth. In the meantime, have a good rest of your week, and see you in the next one. Bye.